Hello everybody, my name is Mustafa and today we're going to be covering Module 8 Friction Practice. So today I want to just address some common misconceptions that I found in recitation regarding normal and friction forces, your friction coefficient, and just drawing free body diagrams in problems that relate to friction. We want to also just go over how to use your equilibrium equations to solve for unknowns. So let's just start with this problem right here. So this one just tells us to draw the free body diagram and not solve for force P. We just want to draw the free body diagram here. And we are also told that this crate is going to be sliding up the inclined surface. So some common misconceptions that I saw here was I saw people drawing the weight negative normal to the surface right here, which will be incorrect. And I saw some people drawing the friction force going upwards. You have to keep in mind that this problem told us that the block is going to be sliding upwards, so it wouldn't make sense for friction, which is a resistive force, to also be going upwards. In that case, you'll just have a block just accelerating upwards, essentially, or you're just going to have a block just being pushed upwards with nothing to resist it. So that's not what we want. Remember, the friction force is always going to be opposite. And I know that we've had problems where you can just draw the reaction forces going in any direction, and then it'll be negative if you assumed wrong. So in this case, you have to assume correct. There's a notation that you have to follow, and it does make a difference. And you might lose points if you incorrectly draw these forces. So you want to make sure you draw these forces correctly. With this problem, we can approach this in two ways. We can draw a coordinate system like this, right, where your x is going parallel to this surface right here. Or what you can do is you can just draw it like this, and I'll show you how to solve for both of them. And how you decide to draw your coordinate system is up to you, as long as you remain consistent throughout. So let's just start with this coordinate system right here. Use a 15-degree incline from the horizontal. And we have our force P. Now, W is always going to be acting straight down, right? Your weight force, it's always going to be acting straight down. The Earth's gravitational pull is not going to change, right? Wherever you are. So that's something that you can keep in mind as you're drawing these. W is always going to be acting straight down, perfectly straight down. And the normal force is going to be acting positive perpendicular to the surface. So in this case, it will be acting this way. Now, as for the friction, we are told that this block is sliding upwards. And usually friction is a resistive force that wants to resist this motion. So basically, if we know that this block is going to be going up, you're going to draw your friction force going the opposite direction. And that's it for the first option here. Let's try the second option with this coordinate system right here. Now, the force P will shift by 15 degrees off the horizontal this way, and your weight will be acting down this way. And I always said that the weight is always going to be perfectly down, but that's only if you consider this coordinate system right here. If you want to shift your coordinate system, you have to shift everything else accordingly as well. So in this case, this is your W, it's going to be shifted 15 degrees off the vertical. But then what you can do is you can just draw the normal force going up like that, and your friction force going this way. Now both ways are correct. Remember, either one of these will get you full points. You just have to keep in mind that if you're going to shift your coordinate system, you have to shift everything appropriately as well. And do also keep in mind that your normal and friction force are always going to be perpendicular to each other. So there's always going to be 90 degrees between them. Now, for this problem, I think the most confusing thing was like where to start, right? You have three blocks right here. So I always like to start with the one with the block that has the force on it, right? So in this case, that would be block B with force P, because that would determine where the friction forces will be on all the other blocks. Because if you start with block A or block C, for example, you might draw an incorrect direction for the friction forces. And then you might realize that by block B, right? And then by that time, you'd have to redraw all these again. And we don't want to do that on the exam when time is very important. So let's just go over this very quickly. We are given weights of 40 newtons, 25 newtons, and 15 newtons for A, B, C respectively. And we're also given the static friction coefficient, and it's 0.3 for all surfaces. Now we want to determine the smallest horizontal force P that will cause impeding motion. So we're going to start with block B. We know that there's a weight acting down here, and we are given 25 newtons for that. we have this force P, which acts to the right. Then, because we know that this block will be pulled to the right, friction will want to move the other way, and we want to resist this motion. So we'll draw both the top and bottom frictions going to the left. We'll say that is FAB, and this is FBC. Now, we are missing the normal forces. We say that there's a normal force acting between B and C here, and then there's a normal force coming from the top block, which is acting downwards, and we'll see why in just a moment. That's going to be an AB. Now we want to draw the block at A. We'll see that this is going to be your NAB acting perpendicular this way. And now, since we correctly guessed FAB going to the left in this one, we're going to be guessing it going to the right on this block, because remember, you want these to be canceling out. So when you switch between blocks, you want to make sure that you're going to be drawing your friction forces and your normal forces going the opposite way. So we obviously we can't forget the weight here, and the weight at A is going to be 40 newtons. Perfect. So now we have everything we need. Let's start solving. And we're going to start with block A actually. So the sum of forces in the y direction here are going to be 40 newtons going down from the weight plus the normal force NAB. So now we can find NAB, which is going to simply just be the weight, which is 40 newtons. And we're going to need this later. Now, moving on to block B, we can do sum of forces in the y direction here. That's going to be negative NAB minus the weight, which is 25 newtons, plus, NBC. Now we know that NBC is going to be equal to NAB plus 25. We know what NAB, we just found it. It's going to be 40 newtons plus 25 newtons right there. Now we can find NBC to be 65 newtons. Finally, we can do sum of forces in the x to find the force P. And we can simply see that there's only three forces acting in the x direction here, which is going to be FAB in the negative direction plus P minus FBC. We can find that P is equal to FAB plus FBC. Now over here, I want to introduce an equation that you might know by now, and if not, you should definitely know this. Your friction force, any friction force, is going to be equal to your friction coefficient multiplied by that respective normal force. So in this case, if we want to find FAB, that's going to be 0.3 as given in the problem, and NAB we have found to be 4 newtons. Likewise for FBC, FBC is going to be 0.3 times NBC, which we have found to be 65 newtons. Now, if we simply plug that in, we'll get 31.5 newtons for P. Now, with problems like these, I want you to try to start your analysis with the block that has the force on it, because based on that, you'll draw your friction and your normal forces. And I want you to, of course, pay attention to your givens first. You have to draw your free body diagrams as always. Don't skip out on that. It's very easy to make mistakes in the middle. You cannot try to solve all of these just in your head. So definitely do write these out. Now, maybe in a problem like this, they might give you the force P and tell you solve for mu. Oh, well, in that case, that's pretty simple, right? You're going to have your force P here, your FAB, your FBC. You're just going to bring this together. This 0.3 will instead be a mu, right? And in that case, you can just solve for mu and just box that answer right down there. So they might tell you to solve for mu. They might tell you to solve for P. They might tell you to even find the normal force. Either way, you follow this process, it should be very easy to find whatever they're asking for, whatever it may be. And finally, we're going to be using moment equilibrium. This is a problem that a lot of people were also confused on. And I think the key point here was that most students thought that this was rotating. That wasn't the case here, and we will see why. The key word here is that the system is in equilibrium. So if the system's in equilibrium, that means that this is not sliding, and it's not about to slide, like it's not close to sliding. So in this case, you can treat this just as a regular block. So here's how we'll solve this. We'll just start by drawing the circle. We know that there's a force P here, and your normal force here. And of course, your friction force, which is always going to be going opposite to your driving force P. And then likewise, we're going to be having a normal force here from the bar above it. And friction force always going to also going to the left because the system is in equilibrium. So what we can do is we can then draw the free body diagram for the bar. So we're given that the bar is 12 pounds. We are also given that the P is 5 pounds. So the force P is 5 pounds. So let's just write those down first. This is going to be 5 pounds and this is 12 pounds. And we also have this normal force NE right here. So all we really get from the bar is that NE is equal to 12 pounds. So what we're going to do here is we're going to use sum of moments at point E and at point F to get rid of all of our unknowns and solve for the friction forces individually. We know that this entire thing is 12.5 inches in diameter, as given in the problem here. And we also have 36 pounds going down here as well. Now, we may not need the 36-pound weight for this problem because it's going on down the line of action right here, but you still want to include this in your free body diagram just to make sure that you get all the points. So we also know that this is 2 inches, and radius is half the diameter, so that will be, 6.25 inches. So taking some moments about point E, 6.25 inches plus 2 inches is 8.25 times P, and P is going counterclockwise, so that'll be positive, minus the entire diameter 12.5 times FF, and this is going clockwise, so that's negative. Solving for FF, we get 8.25 P over 12.5. Now we'll do the same exact thing here, but at point F, this would be 6.25 minus 2, which would be 4.25 for P, and P is acting in the negative direction here. Because we're going about point F, this will be clockwise, plus the entire diameter 12.5 times FE, and this is going counterclockwise. Solving for FE, we get 4.25P over 12.5. Now, plugging each one of these in the calculator, we should expect to get a value of 3.3 pounds for FF and 1.7 pounds for FE. So remember, they can always ask you to solve for the friction force, your coefficient of friction, or your normal force. Always remember this equation as you're drawing your free body diagrams and as you are solving, and keep in mind that whichever one they ask you to solve for, it's all going to be the same. You're just going to be solving for a different variable in the equilibrium equation. And always keep in mind that your normal force is always perpendicular to the surface, not necessarily the horizontal axis. So if you have something that is on an incline, be sure to draw the normal force perpendicular to that incline in the positive direction, not in the negative direction, and not just pointing up. Also keep in mind that your normal and friction forces are always going to be perpendicular to each other. So in this case, the friction can be going in this direction or in this direction, depending on your given problem. And keep in mind that the direction of the friction force is going to matter. Your weight force W is always going to be pointing straight down. Remember that Earth's gravitational pull is going to be the same everywhere, and that's not going to change. And you can also always choose how to define your coordinate system to simplify your solution process, depending on the given problem. So you can draw it this way, like we did with the first problem, or you can just draw the regular one. But either way, whichever one you choose, just always keep the angles in mind and always make sure that you're shifting everything correctly. Now, with any problem where you have multiple bodies on top of each other, I recommend starting by analyzing the shape with the force P. So always start with the shape that has the force, because based on that, you'll be drawing your directions for your friction forces, and then based on that, you want to make sure you also are drawing the correct friction forces and normal forces on the other blocks as you go. So start from P and then work your way from there. Thank you for watching this review video on Module 8, Friction.